we'll be looking at some new information now about optimization. These are max-min problems, and you did max-min when you did single variable calculus. To review, max-min are sometimes called extreme values, and this part we're going to look at on a graph, but not really. You really need to look at the graphs in the lessons because there are many different graphs with a lot of max and min on them so you can see in living color what they look like. Relative max is the highest value at a point if the function value, f of ab, is the greatest value in an open circle around the point. My little picture here, three-dimensional, this would be a relative maximum because it is the highest value, and if you were to look down on it, that would be your point in the middle, and then you've got all the little areas that make it 3D that go down from there. So this is a relative maximum, and you can see the open circle around it. Relative min is the lowest value if the function value is the least in an open circle around it. Now, one thing that is important is that we're not interested in relative max on a boundary. If our function ended, we're not dealing with those. So relative max is not defined at a boundary point. The same way when we defined relative and max and min in single variable calculus, not at an end point. It's the same idea. Now, you can have absolute max also, and absolute min, and they are the max and min on the entire surface. The entire surface. And we're not really, we may find some values that are absolute, but we're not really dealing with them specifically with the notation we have to use here. So we have our absolute on the entire surface, and we're interested in relative max and min. And this section is just visual. You look at it, you see what it looks like, and you decide if it's a max or min. Or you can decide if it's a saddle point. So that's what we'll look at next, is what is a saddle point, and I'll see if I can get something that might show you. A saddle point is a maximum in one direction and a min in the other direction. Now, when you're in space in 3 dimensions, there's a lot of directions. But let's see if we can sort of get an idea of something that might be a maximum in one direction and a minimum in the other. So this point right here would be a minimum. Looks like a bottom of a parabola. But how about if our surface goes down in the other direction? See if I can get this to look kind of right. Nope, can't do it. So a saddle point is a maximum in one direction and a min in the other direction. So this is the minimum. Let's see about a maximum. There we go. That's sort of something. If you look at it front to back, the way I've got this, we have a parabola that opens down. If you look at it from side to side, here I have a parabola that opens up. I call this one my western saddle. Another one that gives you maybe a better idea of the shape of it is in the text, and it's like a Pringle potato chip, where if you look at it in one direction, you have a minimum, and in the other direction, you have a maximum. So we do have a saddle point, and you can see why it's called a saddle point, max in one direction and min in the other. We do have ways using calculus for the multivariable functions to find saddle points, maximum points, and minimum points. But again, in this section, we're just looking at visually on a 3D graph what they look like. In this section, we start studying about optimization. Remember, this means max, min, so on, but this time our extreme values are on a contour map, not on the actual 3D map. Now, your contour maps are going to look different depending on where you see them. This one we're going to pretend is grayscale. I have really dark colors here and here. It gets a little bit lighter, and as I move over here, it's lighter still, and then that's the whitest. Now, sometimes you'll see a grayscale or a blue scale. There's even gold, purple, all kinds of different colors. But you can also see colors. You can see just totally different colors. And if you have colors, they will match a legend. The grayscale or the blue scale matches the legend also, but you're more likely, for example, in Excel, to see colors on a contour map, different colors, and a legend so that you can compare the colors. Remember, these in here are the function values. So that if I'm looking at point A here, it's white, it's a very light color. We consider these lightest colors like on the top of a hill, so the sun is shining down. So if it's a hilltop, and as you come at A from different directions, it's getting lighter as you get to A, so that A would be a relative maximum. Now when you look at B, as you go towards B, the colors are getting darker. B is in the darkest spot. It's like the bottom of a hole or a pit. So you can think of point B as being a relative min. Now let me caution you, this is not enclosed, this white corner. This is not enclosed. So if there's a point in here, we don't know if it's a relative max or not because it's not enclosed in an open circle. So to be sure you have a relative max or relative min, they must be enclosed in an open circle or on a contour map, just in a bounded region. Now point C is a little bit different. It is in the middle of things. As you go from point B, which we said, remember, was a hole, the numbers get lighter going in this direction, but then as we go over here, it gets darker again. So we go up to C and then back down. So in this direction, C would be a maximum. But as I move, say, from point A going in this direction through C, A was a maximum. I get lower to C, and then back here it goes up again to another maximum area. So in this direction, you go down to C and then back up. Well, that's what we had called a saddle point, where it is a maximum in one direction from a low up back to a low, minimum in the other from a high down through it and back up. So C, an area that looks like that between max in one direction, min in the other, is a saddle point. So we can look at a contour map and also determine points that are extreme values. In this lesson, we're looking to find what extreme values might look like in a data table. Remember that our x values of the function go across the top row, and our y values go down the bottom row, go down the column. So that my function f of xy, the x's are here, my y values are here, and my function values for f are in the middle here. So it's the function values that tell us how high or how low, or if there's a saddle point. Remember, a saddle point is high in one direction and then low in the other direction. So with a table, it's kind of difficult because you have to scan and see what you're looking for. So let's go across the row and see what we've got. So I've got negative 15, down to negative 48, back up to negative 31, and up to 0. Okay, so this would be a low point at negative 48. But I don't know what happens when I'm, say, at negative 4. So let's look at the second row. Negative 5, way down to negative 38, back up to negative 21, and up to 10. Negative 7, down to negative 40, back up to negative 23. Well, let's look at this little bit of a column right here. When I went across, these were the low values. if I go up and down this column, I have negative 48, and then negative 38 is a little higher, and then negative 40 is dropping again. So it looks like this point right here might be a maximum in both, a minimum in this direction and a maximum in this direction. Okay? Look at that again. Negative 48 up and then down. Negative 5 down and then up. So it looks like this negative 38 value here, which would be the function value when x is negative 2 and y is negative 2, that looks like a saddle point because it was a max in one direction and a min in the other direction. Let's keep looking. Let's move down again. Negative 15 down to negative 48, back up to negative 31. Negative 23 down to negative 56, back up. Negative 25 down to negative 58, back up. Negative 15 down to negative 48, back up. Okay, it looks like we're still going down to minimums here. But when I look in the middle at this point right here, negative 48 down to negative 56, down further to negative 58, back up a little bit, it looks like this point goes down to that point, but in the other direction, it's still going down to that point. So we're mostly looking horizontally and vertically, but what happens if I go on an angle? Negative 39 down and then back up, negative 23 down and then back up. So for this one, it does go down from all the directions I can see here. So negative 58, which is the function value when x is negative 2 and y is positive 2, looks like a minimum. We'll say local or relative or local minimum as far as what the data table is looking like. Didn't really see one that was just a maximum. We were really looking at the minimum values on this table, which is fine. You never know what you're going to come up with. But that's what it looks like if you try to pick them out of a lot of data. This is a small table, so if it's a bigger table, just look in little pieces like this. Now we're going to look at something that'll be similar to what we did in two-dimensional calculus. It's called finding critical points, and you will remember a critical point as being where max and min occur, max or min may occur. In three space where we have two input variables, a point AB, so that's a particular point in the domain of the function, is called a critical point for the function if either both partial derivatives equal 0 or both do not exist. Now, we won't be looking at the do not exist part, so when we have three-dimensional graphs or functions, even if you don't have a graph, in order to find out where you might have max or min or something new called a saddle point, both partial derivatives have to be solved together as a system. Now, this harks back to two-dimensional space. You have a maximum here, a relative maximum, a relative minimum here, and horizontal tangent line, slope is equal to 0. Well, the slope is the derivative is equal to 0, rate of change is the slope, is the derivative. So we're interested in two dimensions, the xy plane, where we have horizontal tangent lines and the slope is 0. If you have a three-dimensional surface, which I will not attempt to draw at this point, you have a horizontal tangent plane. If you were looking directly through this, imagine it with thickness, and that is the plane that's horizontal. The lessons have beautiful graphs. There are probably 8 or 9 graphs with various points illustrated in 3 dimensions in the lessons, so be sure to look at those. But even visuals don't always tell the whole story. So what we have to do is actually do the calculus with our functions and set them equal to 0. So let's look at some functions now and do the calculus on them. The first function we want to look at, f of xy, is equal to x squared minus 2xy plus 2y squared minus 2x plus 2y plus 1. Finding critical points means we have to find both partial derivatives, partial with respect to x and the partial with respect to y. So let's look at the partial of f with respect to x. Derivative of x squared is 2x minus 2 constant multiplier. My variable for this derivative is x. So the derivative of this x is 1, and y is a constant multiplier, so it stays like the 2. Plus 2y squared, no x involved, and it's not attached at all. This is a constant, the derivative is 0. Minus 2x, the derivative of negative 2x is negative 2, and the derivative of 2y plus 1 is both 0. So this is my partial of f with respect to x, and I will have to set that equal to 0. Now partial of f with respect to y. The x squared term, the derivative is 0 because there's no y attached. Here I have negative 2x, derivative of y is 1, plus derivative of 2y squared is 4y, minus 2x, derivative is 0, plus 2y, the derivative is 2. Derivative of 1 is 0, and this is set equal to 0. So to find a critical point, I take both partials, set them equal to 0, and solve the system. These are solved together as a system. Now, the nice thing about this one, which doesn't happen often, is that I can look at those as a system. Think about matrix systems of equations, and the x's have the opposite sign. I can just add. I can say, okay, let's just treat this as a system and add these two equations. I add these two equations, I get 0. Negative 2y plus 4y is 2y. Minus 2 plus 2 is 0, equal to 0. Now, you may be more comfortable moving the constants over to the right-hand side. It doesn't matter. This tells me that basically y is equal to 0. Okay? I have a y value for my critical point, but there's no x. Well, to get the x, I go back to either equation and find y. Let's look at the first one. My first equation here, 2x minus 2y minus 2 equals 0. Plug in y equal to 0. I think I'm going to go ahead and move the 2 over. I add it. I now have 2x equals 2. So that tells me that x is equal to 1. So my critical point for this problem, for this function, the only point I've got is x equal to 1 and y equal to 0. Now, I could find the z value or the function value by plugging back in here. We don't need to do that because my question just said, find the critical points. We'll look at how this relates to max and min and saddles in another lesson. There are so many different ways to find critical points. This is just one of several. So I'm going to do more examples just to show you some of the calculus or even algebra involved in finding critical points. So let's look at another one. Now here's a scary looking function. Exponential f of xy is equal to e raised to the power negative x squared minus 2y squared. So we have to do our partial derivatives. Partial of f with respect to x. Okay, if it's an exponential function, the derivative is part of the original function. And then, because of the chain rule, you have to multiply by derivative of the exponent. Well, this is two variable functions, so with the derivative is with respect to x. The derivative of negative x squared is negative 2x, and the derivative of this 2y squared part is 0. So this is the first partial derivative. See, that wasn't so bad, right? Okay. And we set it equal to 0. Let's do the partial of f with respect to y. Again, the derivative of e to the u is e to the u and then times the derivative of the exponent. So I repeat, e to the negative x squared minus 2y squared. And now multiply by the derivative of the exponent. The x squared goes to 0. Minus 2y squared is negative 4y. Don't forget, you have to include the negative, the subtraction here. And that's all I have. If I had more terms over here for either x or y, my derivatives would be bigger than negative 2x and negative 4y, but they're not. So we're back to a point again where we've seen this before and many times in two-dimensional calculus. Two things multiplied together to give you 0. Each piece has to be set equal to 0. This negative 2x is the easy part. If I have negative 2x equal to 0, x is 0. That's fine. This, the exponential. Remember that this e is just a number raised to a power. If you take 2 to the third, or 2 to the negative 1, or 2 to the 0, you keep getting a number. It's the same thing here. The number we get is not 0 ever. So this piece is always positive. It's never equal to 0, so it does not come into the critical point search. The only critical point we get from this first partial here is x equals 0. Now the second one down here, the partial with respect to y, we do the same thing. Negative 4y has to equal 0, which gives me y equal to 0. This piece, always positive, doesn't come into play. So the only critical point that I have for this function is x equals 0, y equals 0. Our function in this example is f of xy equal to x cubed plus y cubed minus 3x squared plus 3y squared. So let's look at our partial derivatives. Partial of f with respect to x, the derivative of x cubed, 3x squared, y cubed goes to 0, minus 6x, 3y squared goes to 0. So I have 3x squared minus 6x, I set that equal to 0. Well, let's see, let me go ahead and just do that under here. And I want to try to get some x values for this. So let's pull a 3x out. Even though it's squared, it's not one of those, I need two parentheses where you have to FOIL things. I just pull out the common factor. What's left in the first piece is x minus, I pull the x out, 3 out of 6 gives me a 2 left. So I let each piece equal 0, and from this piece I get x equals 0. From this piece, I get x equal to 2. So I have two values for x. And now let's look at the partial of f with respect to y. The x cubed goes to 0. The derivative of y cubed is 3y squared. 3x squared goes to 0, plus the derivative here is 6y. Very similar look to it, except it's in terms of y. So if we set this one equal to 0, I can factor out 3y. I have y plus 2 left. From here, I get y equal to 0. From this piece, I get y equal to negative 2. Well, I got x's here, I got y's here. What do? You pair them up. So let's look first at x equal to 0. If x is 0, I have two possibilities for y. So one is that y is equal to 0. And the other possibility when x is 0 is if y is equal to negative 2. You're not, well, you are. You're sort of taking this x equal to 0 and distributing it with the two y's. If x is equal to 2, I can have y equal to 0. Or if x is equal to 2, I can have y equal to negative 2. So I have 4 separate critical points for this graph, or this function. And as I mentioned earlier, there are some really nice three-dimensional graphs in the lesson. So do be sure to look at those. They have the dots on them that show you where the different points that these refer to occur. What we're going to do in this lesson now is actually find the extreme values and saddle points using the second partials test. So we have found the critical points, and to do that, we have to take first partial derivatives equal to 0. Partial of f with respect to x, partial of f with respect to y, solve them together. The second partials test is sort of like concavity in functions of a single variable. Concavity can tell you if it's concave down, you have a maximum. If it's concave up, you have a minimum. And so the second partials test gives us an idea of that. Now, the function is often called the discriminant. It is d, and I'm going to say the point AB because I have found my critical points and I plug them into d. D is equal to the partial of f with respect to x twice at the point, multiplied by the partial with respect to y twice at the point, and then you subtract the mixed partial at the point squared. So you square it first and then subtract. This is called the discriminant, and it will tell us whether we have max, min, saddle point, or neither, not neither, but that we can't have any information. So first of all, our first possibility is that D is positive. D is positive. There are two parts to that. If D is positive, we have relative extrema of some sort, max or min. First, if the second partial of x at that point is positive, think back with concavity. If the second derivative is positive, your function's concave up. I picture this. You have a relative min. So you have a relative minimum if your partial of f with respect to x, and then with respect to x again, is positive, you have a minimum. If that second partial with respect to x is negative, this time I think of it as concave down, then you have a relative maximum at that critical point. That's why we have to take the partial derivatives and then plug in our point. The second piece, if D is negative, then at that point, there is a saddle point. The third possibility is that D is equal to 0, and then the test gives no information. In that case, you'd have to try perhaps graphing it in 3D and zooming in on the area you're looking at. But this is our second partials test, and we will use it to help us find the extrema. So let's look at examples now so that this will make more sense. I'm given a function, f of xy equals xy squared minus 6x squared minus 3y squared. You should recognize that function from the previous lesson. We found the critical points there by taking partial of f with respect to x and setting it equal to 0, and the partial of f with respect to y and setting it equal to 0. And these are the critical points that we found. We had to pair them up between the two functions. Remember, you saw these as a system. But now that we have them, how do we know what's a max or a min or a saddle point? Well, that's the discriminant, and so I need to continue into the second partial derivatives. Second partial with respect to x, the y term goes to 0, that equals negative 12. While I'm over here, I want to find the second partial that's with respect to x and then with respect to y. So back here, I do the derivative with respect to y, and it gives me 2y. My second partial with respect to y, for the second time, y is the variable, derivative is 1, so that's 2x, minus, and the derivative here would be 12. So I have fxx, fxy, fyy. The discriminant says pick your point. So let's start with a point 0, 0. Now, I think I won't actually start with this. I think what I'm going to do is go point by point and find out what my values are. So let me write my partial with respect to y down here. And I don't need the first ones anymore. Check each point. So at the point 0, 0, if I plug 0, 0 in here, it's a constant. If I plug 0, 0 in for the mixed partial, it's a constant. but this time, not a constant. I plug in 0, 0, only for y I get 2 times 0 is 0. Plug in here, x equals 0 minus 12. So for this point, I've got my values. The discriminant says, check your point, by multiplying fxx times point. Fyy minus fxy squared. So if I'm checking at 0, 0, fxx is negative 12, fyy is negative 12, fxy is 0 squared. Negative times the negative means that is a positive. I have an extremum if it's positive. What is it? Well, fxx here equals negative 12. fxx is less than 0. My concavity brain. Less than 0 means concave down. I have a relative maximum. So at my point 0, 0, I have a max. And you have to test the discriminant in each of the other points. So let's go to 3, 6. fxx is still negative 12. 2 times y is 6. That is now positive 12. 2x minus 12. 2 times 3 is 6. Minus 12 is negative 6. So to test those values in the discriminant function, I'm testing 3, 6. fxx was negative 12. fyy down here was negative 6. Minus fxy is 12 squared. Positive times the positive, but here I have to actually look at my numbers. 6 times 12 is 72. Minus 12 squared is 144. That is negative. When D is negative, that indicates that 3, 6 is a saddle point. So back up here, I can mark that my 3, 6 is a saddle point. Now, when you look at 3, negative 6, let's see how that's going to vary, if at all. fxx is still that constant, negative 12. fxy is 2y. I plug in negative 6, I get negative 12. fyy is 2x minus 12. Well, x is still 3, so 6 minus 12 is still negative 6. So if I do the critical point 3, negative 6, fxx is negative 12, fyy is negative 6, fxy is negative 12, but I square it, so it also will become 144. Now remember, you square before you subtract. Very important point. And I have 72 again. This is still negative, so I have another saddle point here. So for the graph that I have, and you can see that in a lesson, this particular one has 2 saddle points and a max at the only 3 critical points that we get. Here we have a function that is always a scary one. F of xy equals e raised to the power negative x squared minus 2y squared. In the previous lesson, we found the critical point 0, 0 by taking the partial with respect to x, e to the power times derivative of the power, set it equal to 0. Partial with respect to y, e to the power times the derivative of the power with respect to y, set that equal to 0. But for the second partials test, to determine if our critical point is a max or a min, we have to have second partial derivatives. So to get the second partial with respect to x requires product rule. So our product rule says I have a first function and a second function. So I have First times derivative of the second plus second times derivative of the first, or whichever way you think of it. So, first, e to the negative x squared minus 2y squared times derivative of the second, that would be negative 2, plus my second, negative 2x, times derivative of the first. The derivative of the first is e raised to the power times derivative of the power with respect to x, which you will notice is that. Remember when I do second times derivative of this, all of this is derivative of that. So just be real careful. Now, you can simplify. I tend to do that because I have an e to the x squared here and here, well, an e to the u here and here. You don't have to do that. Our critical point is 0, 0. I can, if I want to right now, find the value of that at 0, 0. So I have e to the negative 0 minus 0 plus negative 2 times 0 is 0 times my e to the 0, which I found is 1, times another 0. This goes away very quickly. Getting the derivative is not easy, but substituting the point in is. So here I have 1 times negative 2 plus 0. So my partial with respect to x twice at the point is just equal to negative 2. Right? So let me go, and I'm going to put that up here. I don't need that piece anymore. So fxx at 0, 0 equals negative 2. Okay? Now let's look at the y. Product rule again. So I take my first function to get my f y, negative x squared minus 2y squared times derivative of the second is negative 4 plus the second, negative 4y, times derivative of the first, and I have my derivative of the first again right here, times negative 4y. And I can substitute in. I did first times derivative of the second, which is with respect to y, plus second times derivative of the first. E to the 0 times negative 4 plus 0, e to the 0 is 1 times 0, makes this one equal to negative 4. Fy equals negative 4. Now I'm going to have to go back and look at my partial with respect to x because I have to do my mixed partial. That was my first partial with respect to x. And from this derivative, I do the mixed partial. With the product rule again, or not. Let's try the product rule. First, that's a squared, times derivative of the second, wait, this is with respect to y. The derivative of this piece is 0. Plus, second times derivative of the first. Derivative of the first, e to the negative x squared minus 2y squared times derivative of the exponent with respect to y, 0 minus 4y. This whole piece goes to 0. Now, that's because I didn't really need to use product rule because the negative 2x was the constant multiplier. But it doesn't matter because this piece goes away anyway. So you don't have to worry too much. We're on a swing. We did product rule, so it's fine. So now let's put the point 0, 0 in here. That's all 0 plus this is 0. Well, e to 0 is 1, and that's 0, and so it's 0. Okay. So we've done all this work. And now we have found out everything that we need in order to use the second partials test. Second partials test says D is fxx multiplied by fyy minus fxy squared. So at our particular point, fxx is negative 2, fyy is negative 4, minus, the mixed partial is 0, square it, I still get 0. This is 8, which is positive. If d is positive, I have a max or min. I look at fxx, which is negative 2, which is negative, concave down. What I have is a relative maximum at the point 0, 0. Now this seems a little odd, but at 0, 0, a maximum just means the values are negative at that particular point. Okay? So the derivative was bad, but the result, plugging in the numbers, is fine. In this problem, we have a company that sells televisions. They have two models that we're looking at, Model A and Model B. X is the selling price for each Model A television set. Y is the selling price for each Model B television set. And we're given demand equations for each model, so that Q sub A is the demand in terms of the selling price of both, but it's the demand for Model A based on how much both are selling for. Q sub B is the quantity demanded of Model B sets that are based also on how much each Model A and B sells. So there's a lot of interplay between the selling price for the models and the quantity that are sold. Question says, how many of each model do we need to sell to maximize our revenue? Revenue is price times quantity. The selling price multiplied times the quantity sold. Well, we have two quantities. This is not a simple company. They have at least two pieces of things in their inventory. So we need a revenue for each piece. So let's look at revenue for A, Model A. The price for Model A says selling price is X. I multiply that by the quantity sold for A, which is this, 10,000 minus 10X plus Y. So my revenue for Model A is X multiplied through here gives me 10,000X minus 10X squared plus XY. That's what I have for Model A. Let's look at what I'm going to have for Model B. I think I'll put my Model A revenue back up here. That's a 2. Okay. So revenue for Model B. The price for Model B, Y is the selling price. The quantity sold for Model B, 15,000 minus 10Y plus X. Price times quantity. Distribute the Y through. I have 15,000 Y minus 10Y squared plus X times Y, or Y times X. So that's my revenue for quantity B. Okay, well, let's see if we can put these together. Revenue for A, revenue for B, 15,000Y minus 10Y squared plus XY again. Okay. Two revenues, but it says maximize revenue. So really there's only one revenue. So we add these together. So my revenue function is equal to, well, the only thing that goes together is the XY. So let me start off with my X terms. Negative 10X squared plus 10,000X. Okay, I'll put these in order of exponents. Plus, I'm going to do the Y again. Minus 15, minus 10Y squared plus 15,000y plus 2xy. A long function. Negative 10x squared plus 10,000x minus 10y squared plus 15,000y plus 2xy. That's my revenue. I want to maximize it. Max-min problems. I have to find critical points first. So I need to find the partial of r with respect to x and the partial with respect to y. With respect to x, I have negative 20x plus 10,000. Nothing here, nothing here. And here's an x. Derivative of that would be 2y. Okay. Now, in a max-min problem, I find critical points, and I have to set each piece equal to 0. Let's look at the partial with respect to y. 0 there, 0 there. Negative 20y plus 15,000 plus derivative of y is 1. That gives me 2x equal to 0. And I have to solve these together. This is a system. Let's see. Well, I've got 20y and 2y and 2x and 20x. So what I need to do is to combine these in some way. Think in terms of a matrix. I have negative 20x here. If I multiply this equation by positive 10, I'll end up with a positive 20x. So let's do that. Let me take my y, multiply it by 10 times the whole thing, and I'll have, I'm going to switch the order. 20x I'm going to put here, plus I multiply by 10 gives me 150,000, minus multiply this by 10 gives me 200y, equal to 0. Okay, so I've multiplied 10 times this one, 10 times this one, and 10 times this one. That was my ry, and now I want to go back and add that to the first equation. Negative 20x and positive 20x, they go away. 10 and 150 is 160,000. Zeros look a little like my 6's, don't they? 0. Plus 2 minus 200 is 198y equal to 0. So 160,000 equals 198y. Y is about, if you divide with your nice calculator or Excel, 808.080808. That continues. That's the y value. Y was B. That's the number of the selling price in dollars. Price for one Model B TV set. Okay, that's what we're thinking of, because you have to go back and think how we defined Y. It's not the number, it's not the quantity, it's the selling price. Okay? So, how do I find X? Well, to find X, you have to put this number back in. Actually, either of the equations will work. I've got this one up here. If I put this in, let me go back and do negative 20x plus 10,000 plus 2 times y, 808.08 equals 0. Add these together, divide by 20, I end up with x as about 580.81. This one also continued 08, 08, 08, but I rounded to get 1 because this is $580.81 is the selling price for a Model A TV. So I've got these as, this is what I've got for my values, the selling price for each. In order to find out how many of each I sell, I have to go back up into the quantity, my Q's, which I have erased, of course, my quantity, and plug those in and find the quantity. If you take your quantity sub A, plug in your x and your y, you end up with about, I want to say about 5,000. I think it was like 5,007 or something. And quantity B is about 7,500 if you put in the x and y, because you need both. This is x, this is y. And you need them both in the quantities, and that's about how many you sell. From this, you can also determine what the revenue would be. Now, we're assuming it's maximum revenue because that's what the question asked for. You can do the second partials test and come up with exactly the same thing that you need. Okay? If I do the second partials test, my R sub x was negative 20x plus 10,000 plus 2y. I would need the second derivative. Second derivative with respect to x is negative 20. It goes very quickly. While I'm here, let me do the mixed partial from this x. 0, 0 would be 2. The derivative with respect to y, 0, 0, negative 20y plus 15,000 plus 2x. My second partial of the y, negative 20 and zeros. So the second partial test doesn't have to take a long time. So D at my point, 808 for y and 580 for x, turns out to be negative 20 for the fxx times negative 20 for fyy minus 2 squared minus 4. 400 minus 4 is definitely a positive number. We look at, I call this x instead of r. R at my point where x was 580.81 and y 808.08. X is negative 20. Negative 20. Less than 0, which indicates a maximum. So the problem said, what do you need to sell for maximum revenue? We found it, and the second partials test verified what our assumption was. We got one critical point, and it worked out, as it should. In this lesson, we're going to look at another method to solve problems for optimization, and it's called the Lagrange multiplier method. It's optimization subject to a constraint. This is not just where you want to find the relative max, min, and saddle points of a function in general. This is, we would like to do that, but we're constrained by something. Production level. We can only produce so many items, so that x of one plus y of another has to be less than or equal to the total amount. Or orders. I have an order for 200 chairs and desks combined, and so x plus y has to at most be 200. Or a budget. I have a $16,000 budget, and I have to pay staff, and I have to account for salaries and investment and rent, and there's a constraint for a budget. So there are lots of different types of constraints. Now, the whole idea of this is that a constraint lowers your max. So the lessons show you one way to solve with the substitution method, and we're going to look at the Lagrange multiplier, which takes the constraint and looks at it by introducing a new variable called lambda. This is a picture of a contour map of a function. So remember, each of these contours are a function value. So this could be f equal to 2,000. This may be f equal to 1,200. This might be f equal to 600. So these are contours of constant function values. This blue line is our constraint. And you'll notice that the constraint is tangent to this contour 1,200 at this x value and this y value. What this tells us is everything that's along that constraint, we use up everything we've got. Everything that's underneath here, every x and every y is affordable because we have not reached the constraint yet. Everything above it, up here and out here, is not affordable because we've gone beyond what the constraint says. What we want to look at is using every bit of the constraint. That's what the Lagrange multiplier method does. And where the constraint is tangent at that x and that y value, that's where our max occurs. So let's see how we can actually do that with our calculus. The constraints that we're going to talk about will form a function. And we'll say that function is, the constraint is the function g of xy. And we will make it so that it is set equal to 0. And there will be 3 equations that we use with this method. The first equation will take the partial of our function with respect to x, set it equal to lambda times the partial with respect to g of xy, this function here. So that is lambda, Greek letter. Our second equation, partial of f with respect to y, we set equal to lambda times the partial of g with respect to y. And the third equation is the constraint equation, g of xy, set equal to 0. So when we get our functions, we use our partial derivatives, set up a system of 3 equations, and solve it together. Let's see how this really is going to work. In this problem, we're asked to find the minimum value for the function f of xy equals x squared plus 2y squared minus xy, subject to the constraint 2x plus y equals 22. So we have a limited amount of x's and y's to equal 22, so that's going to affect our maximum value. The formulas that we have to work with for the Lagrange multiplier method say I need to find the partial of f with respect to x, partial of f with respect to y, and this function will form our constraint, and we need those partials. So my partial with respect to x is 2x, that's 0, minus y. Partial of f with respect to y is 4y minus x, and I do not set those equal to 0. I need my constraint function. Well, the constraint function is supposed to be written as g of xy equal to 0. So my g of xy function would be 2x plus y minus 22 set equal to 0. And I get the partials here. The partial of g with respect to x would be 2. Partial of g with respect to y is 1. And the 3 equations I'll work with are the partial of f with respect to x equal to lambda times the partial of g with respect to x. Partial of f with respect to y equals lambda times partial of g with respect to y. And my constraint equation set equal to 0. So let's see what we have. Partial of f with respect to x is my first equation. 2x minus y set equal to lambda times the partial of g with respect to x, which is 2. My second equation, the y's, partial of f with respect to y is 4y minus x equal to lambda times the partial of g with respect to y. And my constraint equation is this one up here. I'll just go ahead and call that number 3 up there. Now, generally, what we do for these problems, we solve the first 2 together as a system. We'll get a relationship. To do that, I'm going to take my partial on the left and divide by 2 so that it's equal to lambda. So my first equation will be 2x minus y over 2 equals lambda. I want to set that equal to the second equation, which is already lambda. Lambda times 1 is lambda. 4y minus x. So I have combined the first and second equations into this little relationship equation. To solve this, I'm going to multiply across by 2. 2x minus y equals 2 4s are 8y minus 2x. And rearrange them with some algebra to get, let's say, y equal to something. Move this y over here, gives me 9y. Move my 2x, adding it over here makes it 4x. And I can either say x equals 9 over 4 times y, or y equals 4x over 9. So you can solve it either direction, doesn't matter. You always get something like this, x's and y's. You don't get numbers. That's where the third equation comes from. My third equation is the constraint, 2x plus y, and you can either say minus 22 equals 0, or you can say equals 22. You can use it any way you need to. And I know that y is in terms of x. So I have 2x plus my y is, I'll say 4/9 x, and then equals 22. I tend to do fractions. I like common denominators. So if I want 9 on the bottom of both, I have to multiply this by 9, gives me 18x, which is conveniently 22x over 9 equal to 22. So when I go to solve that, I will multiply both sides by, go under there, 9 over 22. I have the 22, multiply by 9 over 22, gives me x equal to 9. They don't always come out that neat, but this one did. I have x. What was the question? Find the minimum value for the function. I need y. Here's y. Whenever you have one variable, you just go right back up to the relationship, and y is 4/9 times x. X is 9, y is 4. So this is the way, the easiest way to find the other value of the variable. The question, the original question said, find the maximum value of the function. The maximum occurs, minimum value occurs when x is 9 and y is 4. So I take those values and plug them in. 9 squared plus 2 times 4 squared minus 9 times 4 comes out to be 77, I think. That's 81, and 32 minus 36 gives me 77, 4 different. So I have found a minimum value of the function and where it occurs using the Lagrange method with a lambda. This is a function about the sales of an item or items that a company produces. The sales, 10 times x raised to the 0.2 power times y raised to 0.8 power. Those are the weekly sales based on the amount of spending on newspaper ads and television ads. There's a $50,000 budget. A unit for a newspaper ad is $35. That could be column width, column length, column width. TV ads are $55 per unit. That could be, the unit could be a 15-second slot, a 30-second slot, a minute slot, whatever. But these are the per unit prices. To reach our budget, I can't just go x plus y equals 50,000 because x is $35 each unit. So my budget has to be 35 times x plus 55 times y equals 50,000. As an aside, sometimes you'll see a constraint that would say maybe x $1,000, but the 1,000 is written in words. Well, it would be the same idea. You would have to multiply 1,000 times x, or 1,000 times y if it's called x $1,000. Okay? So this is our budget. This is our constraint. Since there is a constraint, we have to use the Lagrange method to solve this system, or this problem. We want to certainly maximize the number of sales per week. Okay, well, let's see what we have to do here. We have 3 equations to do for Lagrange. The first one says, take the partial of f with respect to x. Right here, okay. Partial of f with respect to x. 2/10 comes around times 10, gives us 2x, and I subtract 1, gives me negative 0.8. Okay. Actually, I think I'll do it as my standard student. Now, let me keep that. That'll work. 2x to the negative 0.8. And the y stays constant, positive 0.8. We're going to find it most useful not to use negative exponents. So I want to rewrite that derivative as 2y to the 0.8 over x to the 0.8. My partial of f with respect to y, the 0.8 comes around front, gives me 8x still to the 0.2, and y, when I subtract 1, is negative 0.2. So again, I'll move it to the bottom. 8x to the 0.2 over y to the 0.2. Now, those are the partials with respect to f. I need my partials of g. G of x, y is the constraint function. To set it equal to 0, I'd move the 50,000 back over to this side and subtract. My partial of g with respect to x is 35. My partial of g with respect to y is 55. And I need to combine these. So if I take my 2y to the 0.8 over x to the 0.8, this was the partial with respect to x. That will be set equal to lambda times the partial of g with respect to x. This is my partial of f with respect to y. I want to set that equal to lambda times the partial of g with respect to y. When I do this, I don't just have them equal to lambda. I need to divide by the 35 and divide by the 55 so they're both equal to lambda. And when you divide, this 35 just goes in the denominator as a multiplier times x. So I have 2y to the 0.8 over 35 x to the 0.8, and that would be equal to lambda. And my second equation, if I divide by 55, I have that equal to lambda. So these are the two equations set equal to each other. 8x to the 0.2 over 55 y to the 0.2. Now we get to cross multiply. So I've got 2 y to the 0.8 times 55 y to the 0.2. But notice what you get here. 2 times 55 will give me 110. But I add the exponents on the y's, I get y to the first. So this side is actually 110y. Big change here. When I multiply over here, I'll have 8 times 35. 8 5s are 40, 8 3s are 24, and 4 is 28. And x to the 8/10 times x to the 0.2, add exponents, you get x. So y is 280x over 110, and I can divide out the zeros and have y equals 28x over 11. This is what now goes into my constraint. And you can leave the constraint like this, or you can rewrite it minus 50,000 equal to 0. Let me write 35x plus 55 times y, and y is 28 over 11x, equals 50,000. I need to do all of my magic, putting things around here. 35x plus 55 times 28 is 140. X over 11 equals, that's next, 50,000. Multiply across by 11. This gives me, that's not 140. 140 is what you get when you multiply and divide. Sorry about that. I was right. Okay. 35x plus 140x gives me 175x equals 50,000. So my x turns out to be about, when you divide and round, about 286. And then I put that back over here to get the y. So my y is equal to 28 times 286 over 11, which turns out to be about 727. So that's how the rounding issue comes out. And that's actually what the question asked, because the question said, what do we want to do for newspaper ads and TV ads? And so you clearly don't want to spend nearly as much on the newspaper ads. They're cheaper, but you only need 286 units. And for TV ads, you get more bang for your buck. So you spend more money, but I suspect you get more visibility on television these days.